So we began this chapter with the question of computing areas. How do we compute areas? We saw that you can do that by the definite integral, but we haven't really had a convenient way to compute the definite integral other than through the Riemann sums, which, as you saw, was quite tedious and difficult. And so now we come to the second part of the Fundamental Theorem of Calculus, and this is what it says. So if you have a continuous function, little f is a continuous function on a closed bounded interval, then for any antiderivative, big F of little f, the definite integral from a to b, which of f dx, which when little f is above the x-axis, you can interpret this as area. This is nothing other than big F of b minus big F of a. You just use an antiderivative of little f, and you plug in the top bound, subtract, plug in the bottom bound. I do want to take a moment and just show you why this is true. You don't have to know this necessarily, but it's really nice if you can. So why is it true? Well, recall our function g of x, which goes, let's just say, from 0 to x of f of t dt. G is an antiderivative of little f, and any antiderivative of little f is actually going to be just g up to a constant. And so actually, if you want to get the area between 2 points, here's a, here's b, here's your f of x. If you want to compute this area using g, then this is just exactly g of b minus g of a, like we did before. You take the area from 0 out to b, and then you subtract the area from 0 out to a, and you're left with the area that you want. And so this actually works for any antiderivative. And when you look at it this way, it doesn't seem so grand, but actually this is a really wonderful result. And let's take a moment and just see how it can make our life a little bit easier. So, for example, we worked out the integral from 0 to 1 of x squared using a Riemann sum. We had little rectangles flying around and ends going everywhere, and we ended up computing that the area under x squared from 0 to 1 was exactly 1/3. Now let's use the fundamental theorem. Let's realize that big F of x equals x cubed over 3 is an antiderivative for x squared, right? You can check that big F prime is x squared. That's what we need. And so this integral is just big F of 1 minus big F of 0. Big F of 1 is 1/3, big F of 0 is 0. And so, wow, that was a lot easier. Oh my goodness. You just plug it into your antiderivative and evaluate. So let's do another problem. So maybe we want to find the area under sine of x from 0 to pi. So here is the piece of area that I want, and I need to realize that this area, because sine is above the x-axis, this area is exactly the integral 0 to pi of the sine of x dx. I don't want to slice up the x-axis into lots of little pieces and try to compute a Riemann sum. I do want to realize that if I take big F of x equals negative cosine of x, then what? Big F prime is minus sine, which is just sine. And so minus cosine is an antiderivative, so this is equal to minus cosine plug in pi, subtract minus cosine plug in 0. Cosine of pi is minus 1, so I get a minus 1 is 1. And then cosine of 0 is 1, so I get a 1 plus 1, which is 2. And so this little piece of area is exactly 2. All right. On a similar note, what happens if we just change the bound from pi to 2 pi? Please don't reinvent the wheel too much. You've already found the antiderivative, so you just use it again, and you say, well, this is just, we'll often write this like this. Let me show you a different notation. This is just minus cosine of x evaluated from 0 to 2 pi, and this evaluation bar means plug in 2 pi, subtract, plug in 0, and you're plugging those into this function. So this is just minus cosine of 2 pi minus cosine of minus cosine of 0. And of course, that's just 1 minus 1, which is actually just 0. So here the what's happening, if you want to look at the picture up the top, you're going all the way back to 2 pi, and the negative area here is canceling out the positive area there, and you just get 0. So I wanted to do a useful fact with you. We'll do one more example as well, and then we'll stop this video. So let's assume that I have a function f that's greater than or equal to a function g of x, and I'm interested in finding the area between these two functions. So scroll down here. Maybe I've got some point x equals a over to some point x equals b. This a and b might be where f and g intersect. Maybe not, but I want to compute this area between them. So how do I go about doing that? Well, you just integrate top curve minus bottom curve. That's the big takeaway. Let me write that down somewhere. So the key here is top minus bottom. We'll just say that. And you want to integrate that. Why? Well, when you integrate from a to b of f, you get this big area. When you integrate from a to b of g, whoops, I made it very messy, but you get this area. And so when you subtract the big area minus the lower area, what's left is exactly the area that you want. So the key for finding the area between two curves is to integrate the top function minus the bottom function, paying attention to which one is on top, which one's on the bottom. So let's find the area bounded between y equals x cubed and y equals x. So we'll start by graphing this. Let's graph it. Okay, so x cubed does something like this. Y equals x does something like that. So there's actually going to be two pieces of area bounded here. And I want the total area. I don't want negative area. I don't want to think about this as like negative area canceling out by that. I want this area. And so I need, for the first piece, I need to have the top curve minus the bottom curve, and the other piece of area, I need the top curve minus the bottom curve. So you can actually solve where are these curves equal. X cubed equals x. You get x cubed minus x is 0, so we get x. X squared minus 1 is 0, so I get x times x minus 1 times x plus 1 equals 0. So the intersection points are happening at 1, and then at -1, and then at 0. And so now for the total area, I can write that down. I just get, well, the area of the first piece. Let's just say the total area is going to be a1 plus a2. And let's make this area a1 and this area a2. The a1 area is going to be the integral from 0 out to 1 of the top curve, which is just x, because that's the curve that's on top here, y equals x, minus the bottom curve, minus x cubed dx. That's area 1. And then, by the way, area 2 is going to be the integral from, we're going from -1 to 0, so -1 to 0 of the top curve is actually x cubed in this case, minus the bottom curve, x. And so we end up with these two things. So now we need to find an antiderivative. So the way that we usually write this is you just write down your antiderivative. So I know that the antiderivative of x is going to be x squared over 2 minus the antiderivative of x cubed is going to be x to the 4th over 4. And then I want to evaluate this from 0 to 1, which is going to be 1/2 minus 1/4, which is going to be 1/4. Symmetry suggests that these areas ought to be the same, but let's work it out and just check it. It's good practice. So for this one, I'm going to get the antiderivative is x to the 4th over 4 minus x squared over 2, evaluated from -1 to 0. So first you plug in 0, you get out 0. By the way, up here I did the same thing. I plugged in 1 and I got 1/4, but when you plug in 0, you get 0 minus 0. So hopefully that was clear to you. Okay, let's plug in 0. We get 0 minus 0, so that's gone. Then we subtract and we plug in -1, and so I get 1/4 minus 1/2. So I have, okay, 1/4 minus 1/2 is -1/4. I get -1/4, which is again 1/4. And so the total area, the area between y equals x cubed and y equals x is 1/4 plus 1/4, which is 1/2. So that's the area that we wanted. So anyway, when you're doing area problems, you have to be careful how you set up the integrals. You want to make sure that the top curve is indeed on top. All right. So I'm going to stop here, and you have what you need to do the problems from 5.3 and 5.4.